So a point estimate is the best estimate we have of a population parameter. Like for the population parameter mu, our best point estimate was x bar. It comes from the sample. For standard deviation, population standard deviation, our best point estimate was the sample standard deviation. Right? For the population proportion p, our best point estimate was p hat. Okay, so sometimes we have to use those values if we don't have the other types of values. All right. And so we're first going to look at the point estimation of a population mean. All right, so your book says that an estimator is a strategy or rule that is used to estimate a population parameter. If the rule is applied to a specific set of data, the result is an estimate. Okay, so if we use one of these point estimates, then the result that we get is going to be an estimate because we're trying to apply it to a population. That will be like, let's say that I took your test average on test 3. And then I told every class from now on that I ever teach statistics to, hey, on my test 3, the class average is a 95 because that's what I want your test average to be, by the way. So I want your class average to be a 95. That would make me happy. All right, I'd be very, very happy. But if I use that to predict and say, well, hey, test 3 is not too bad because all of my classes that I'm ever going to teach, are going to average around a 95, then I'm using a sample value, point estimate, to make draw conclusions or maybe forecast or predict how all of my other classes are going to do. Now, this may be the best class that I ever have, so maybe y'all are just going to set the bar way up high. But that's one way that we can use estimates. Okay. Now, if I'm making an estimate though, I probably want to have an interval for that estimate. So I could say something like, let's say that your class average was around that 95, and I could say, well, I'm pretty confident that my future classes are going to make between 80 and 100 on this test. Now, how confident could I be that the actual average would be between 80 and 100? Well, I don't know. Maybe I'm 80% confident or 90% confident. I'm just throwing numbers out there, but we're going to have to use this type of stuff to figure out our intervals. I'm about 95% confident that the class average will be between, say, a 70 and 100, the whole average. So I don't think my class average on a test in here will be below a 70. That doesn't happen very often in my statistics classes. Believe it or not, about 75% of the people in this class will have an A. That's usually how it goes, whether it's on ground or online. But I'm really confident that the average would be somewhere between a 60 and 100. Okay? Well, how confident would I be, say, that the average would be between a 90 and a 95? I might not be as confident. I might be about 60% confident. Because I'm using values that I've gotten from you, from your data that I've gotten from taking your test average for the whole class, and I'm trying to estimate in the future where the true value is going to lie. And so the bigger the interval, the more confident I am. The smaller the interval, the less confident I am. All right? And that's basically, I mean, that's kind of like the in layman's terms, what we're going to be doing. And we're going to do that for a mean. We're going to do that for proportion. We're going to do that for a standard deviation. The concept is going to be the same for all three. And that's the next, after we go over this section, the next three sections are about making interval estimates for a population mean, a population proportion, and a population standard deviation or variance. Okay? So the formulas may be different, but we're doing the same thing every time. So if we can get the concept of what we're doing early on and we understand it, it's going to help us in those other sections. Sometimes to the point of where if you have the formulas and I teach you how to do it for the population, you may be able to go and just get the formulas and do the other sections without me even explaining it. But, you know, I'm not going to do that. I'm going to go over it anyway. All right, so let's just look. There's in your PowerPoint, you know, hopefully everybody has a copy of the PowerPoint. That I make reference to that a lot. You can see the point estimators that are there. I've written them down. It gives you a point estimate, like an actual, what would they look like? This is, like it says, X bar equals 12.7. It says P hat equals 0.37. So it's like those values that we're used to using when we're doing our z-scores and all, finding our probabilities. So it's those types of things that we were using in our formulas. All right. So we have something called a mean squared error. And this will help us if we wanted to figure out like a margin of error type deal. And the mean squared error, MSE, this is also in your PowerPoint, of our point. This is the point estimate for the mean, right? This is sample mean. So this will be a point estimate for the population mean. The mean squared error is equal to the error of X bar minus mu squared. All right, so it says an estimator's average squared distance from the true parameter is referred to as the mean squared error. The mean squared error for the sample mean is given by that, okay? That formula that I just gave you. So what do you think a perfect estimator, what do you think its mean squared error would be? Or what would we want it to be if it was perfect? We'd want it to be 0. We would want our margin of error to be 0. But that, in reality, that's not going to happen. Do you think because your test average on test 3 is a 95, that every test 3 that I give in statistics is going to be a 95? No. In reality, it would be not quite 0, maybe not even close to 0. I don't know. Maybe I teach better one year. I'm a better teacher because I'm learning every year. And then maybe I'm sick one year, and like I'm sick the whole semester, and I try to teach as good as I can, but my skills just aren't there, and I can't teach that good. So then maybe that class doesn't perform as well. Because that's how I base off of how good I teach is how good you do. Okay? Just remember that. I mean, I believe that's how every teacher should teach. How good I teach is based on how good you do in my class. Even though there's other factors that go into it, you know, I would want that mean squared error to be as close to 0 as possible. All right. So the type of estimators that we're going to use going forward, we want them to be unbiased estimators. We've already talked about what an unbiased estimator is. Because we want it to be a true representation of the population, or as close to it as possible. Your PowerPoint, the last slide here says, as we've previously discussed, to be an unbiased estimator, the expected value of the estimator must be equal to the parameter that is being estimated. Among unbiased estimators of the population mean, the sample mean has the smallest mean squared error. So it would be then the most unbiased estimator. All right, so now we are going to look at how to calculate the interval estimation of the population mean. All right, so to calculate this actual estimation, we are going to have to figure out a couple of more variables to, depending on how confident we want to be in our interval. It's actually called a confidence interval, okay? One of those values that we're going to need to have to figure out how to find that's very critical to what we're doing is called, believe it or not, a critical value. All right? So the formula that we are going to use to form our confidence interval for the population mean, it's in your PowerPoint, but I'm going to write it down. This is confidence interval of the population mean is X bar. We know what that is, right? That's our sample mean, plus or minus Z sub alpha over 2. I know that looks a little crazy. It's a little fish. Z sub alpha over 2 times sigma divided by the square root of n. This is our new magical term here. And us, as far as calculating this interval, remember intervals, we've done that before, like with the empirical rule, how we calculated an interval, like a low number and a high number. We did that in the homework, or Chebyshev's theorem. We calculated an interval depending on how many standard deviations it was away from the mean. Well, to calculate this interval, I need a critical Z value. I need a population standard deviation. That's right here. I need an N, the sample size. And then I need the sample mean. So the only thing new here that we need is that critical value. That is a critical Z value. All right, so I'm going to show you how to find a critical Z value by using our tables. So I am going to find a critical z-value let me pick one. So this is a critical z-value for a confidence level of 0.80. Now, what percentage would that be? What's a percentage for 0.80? 80%. So this is an 80% confidence level, but we can write it as a decimal as 0.80. Okay. Let's see if I can find a table. So you're going to need your z-score table. So go ahead and pull that out if you don't have it. I apologize, this is taking me a second to pull up. So remember, we use that table that is, we use the A table and the B table. If you do look at some of the instructional videos that come with the book, they may show you a different way by using symmetry, and that's okay. However, in general, I don't teach, I always use the symmetry. All right. So for a confidence level, an 80% confidence level, I have to calculate something called alpha. And alpha is equal to still trying to get this to load. Give me 1 second. Alpha is equal to 1 minus the decimal that's associated with 80%. So 1 minus 0.80 is what alpha is going to be equal to. All right, so what is 1 minus alpha? What is 1 minus 0.8? 0.2. All right, does everybody understand that? For an 80% confidence interval, I have to calculate alpha. Remember, there was an alpha in my formula. There was a little alpha right here. All right, so for an 80% confidence interval, alpha is equal to 1 minus 0.80 is equal to 0.2. So if I plug that in to the z, it'd be z sub 0.20 divided by 2. So what is 0.20 divided by 2? Some of you can probably do that in your head, right? That's 0.1. So that would be z sub 0.10. You follow me so far? All I did for an 80% confidence interval is I said 1 minus 0.8 was 0.2, and then I took that 0.2 and I divided it by 2 because that's z sub alpha over 2, which stands for a critical z-value. Now what I want to do is I want to look up an area of 0.1 in my chart. So here's the chart. I didn't say I want to look at a z-value. I want to look up the area to find the z-value. So I want to get as close to 0.1 as possible. So let's look. And what value stands out here? That's as close to 0.1 as we can get. I have 0.1003. So that would be a z-score of what? Negative 1.28. Does everybody see that? Look in your chart. Get as close to 0.1 as possible, and that's negative 1.28. Alright, so that means that my critical z-value is equal to plus or minus 1.28. Let me show you why graphically. So if I was under this standard normal curve, let's pretend that's a bell curve. Alright. I want to know the z-value on either side that would have 0.10 area. So 0.10 area there, and also to the right 0.10 area. What do I get when I add 0.10 and 0.10 together? 0.2, the alpha that I had. Alright, but since I have to worry about a critical value on both sides, that's why I had to divide it by 2. So I'd know what area to look for. Okay, so remember here in the middle z is 0. So what do you think this z-score is here? Is this the positive or negative one? That's the negative 1.28, and this one over here is the positive 1.28. Now let me show you why it doesn't make a difference which one we use in our formula. When we use our formula, if you look at our formula at the top to form the interval, see there's a plus or minus in front of that. So whether I plug in a positive 1.28 or a negative 1.28, it's going to do the same thing because I would take the positive and the negative of whatever I get on the right side. So in general, in textbooks and people that teach statistics, they don't explain that you can use either one. They just tell you use the positive one. And that's fine because our brains work better with positive values than they do with negative values, right? At least mine does. So I would just associate an 80% confidence level with a critical z-value of positive 1.28. Now as far as finding it from the table, it's easier to find the negative one unless you draw this first. And then if I wanted to find the positive one, what would I have to look up an area of? 0.9, right? If you look up 0.90, that would give you a positive 1.28. Now, if none of that makes sense, I'm telling you right now, for every problem that we work with an 80% confidence interval or confidence level, the critical z-value is going to be 1.28. There's a small table in your book that gives, and it's in the PowerPoint, that gives the common confidence intervals. These aren't the ones that are always used, but these are the ones that are most commonly used. All right? It says for 0.80, we use 1.28. For 0.90, we use This is actually a special value, 1.645. All right. And then what do we have? We have a 95%, sorry. We have a 95%. I was seeing if the table was maybe on here. Okay, it is on B. So right here. Good. I was going to copy it up here. So on table B, you can see for 0.80 we use 1.28. For 0.90 we use 1.645. For 0.95 we use 1.96. So I'm going to complete my little table because I started it. I like to complete things that I start. All right, so 0.95 we had 96, and then for 0.99 we have 2.575. Oh, okay, so it has an extra one than your PowerPoint does. So 0.98 is 2.33. And 0.99 was 2.575. All right. This is not every possible imaginable confidence interval ever. But these are the ones that are most commonly used when making population, these confidence intervals for population mean. So if it asks you to use an 85% confidence interval, you have to know how to find it. So how do you find it? You find it the way that I showed you to find 1.28. So let's say that I was working a problem and it says use an 85% confidence level or confidence interval. So what I would want to do, and I'll go back through this really fast, it won't take too long. For 85% confidence interval or confidence level, my alpha is equal to 1 minus 0.85, which is 0.15. My critical z value, z sub alpha over 2, that's going to be z sub 0.15 divided by 2. All right, so that's going to be z sub 0.0 what? 7 5. Is that right? And I can take a calculator and do it. Yes. All right, so what that means is if I look up an area in my table of 0.075, it's going to give me the negative value. So go to my table and look up. I'm looking for an area of negative. Oh no, I'm looking for an area. I can't have a negative area. 0.075. So 0.07. This is as close to 0.075 as I can get. Right? 0.0749. So it is negative 1.44. So negative. So we would use, it would be better for our brains if we use 1.44. So I mean, if you wanted to add that to your little table over here, because that seems like something that would be common, like halfway between 80 and 90, I wouldn't mind you doing that. You can add on to it. So I've shown you how to do it the long way. The easy way is just to look at the table. All right. If you look at your PowerPoints, you'll see they're doing the same thing for all the common values. If you look, I think it's around the 5th slide or so. Yeah. So here's what it shows about the critical values. And it doesn't even give you all the values that are on your table B. It gives you 4 values. So you can see 80%, got plus or minus 1.28. For 90%, we got plus or minus. They carried out an extra place because of where this area is located. So what would this area be? This area would be 0.05 on each side. So if you try to find as close as you can get to 0.05, you can't get, exactly where you need to be. So by using calculus, or even using a calculator that can do the calculus for you, you can come up with this z-score. And then there's 0.95 and 0.99. You find them all the same way. 1 minus the value. You get your alpha, divide it by 2, and that's the amount of area you want on each side. All right. Clear as mud, right? Okay, let's go back. So once we know how to calculate that critical z-value, then everything else falls into place. Okay, then it's just plug and chug, crunching numbers. So let's look at an example. All right, I'm going to put an example up here. This is in the PowerPoint, but we'll work through it. It asks us to do a lot of confidence intervals. I say maybe we'll do 2 of them. It asks us to do 4 of them. Let's do one for 80%, and then let's do one for 99%, just to compare the intervals. All right, a random sample of 100 car engines, so N equals 100, has a mean weight of 425 pounds. So that's the mean from the sample. So that's X bar. 425. Construct, and then it asks us to construct these 4 confidence intervals for the population mean. But we're going to do 80%, and we're going to do 99%. If the standard deviation of the population is 900. So population standard deviation. All right, that's our lowercase sigma is 900. Our formula was X bar plus or minus Z sub alpha over 2 times sigma over the square root of N. All right, so that's what we're going to plug in. We do need the critical Z value for both of these. So what was the critical Z value for 80%? 1.28. So in our formula, we're going to plug in 1.28 for the critical Z. So population mean, the sample mean is 425. So it's 425 plus or minus the critical value, 1.28, times the standard deviation, 900, divided by the square root of the sample. So square root of 100, which we all know is 10. All right. So that's going to be 400. Let me scroll down a little bit. That's going to be 425 plus or minus. If I know that the square root of 100 is 10, what's 900 divided by 10? 90, right? You can do it in your calculator, but that's what you're going to get. So let's say 1.28 times 90. So we have 425 plus or minus 115.2. Now plus or minus means just what it sounds like. I'm going to add it and then I'm going to subtract it, and that's going to give me 2 values. Okay, so First, I'll add it. So 425 plus 115.2, I got 540.2. All right, and then I'm going to say 425 minus 115.2. And I got 309.8. All right, so if I wanted to write this in interval notation, remember in interval notation, your smallest number comes first. So it'd be parentheses 309.8, comma, 540.2. So that's one way to write that answer. All right. Now let's do the same thing, but let's do that at the 99% confidence level. Okay, so we have all the same variables except our critical z-value. And from our table, we know that our critical z-value is what? 2.575. All right, so I'm going to use the same formula. X bar, that was 425, plus or minus, we'll plug in 2.575, times the standard deviation, it was 900, divided by the square root of n, square root of 100. So it's going to be 425 plus or minus 2.575 times 90. All right, so that's 425 plus or minus, what'd you get? 231.75. $231.75, right? All right, so that's what we're going to add and subtract. So first, let's add. And I got 656.75. Now, I'm going to subtract. I got 193.25. All right, so one way I could write that answer, if I wrote it in interval notation, I always write the smaller one first. So that would be 193.25 to 656.75. So the more confident that I want to be that the actual value will be there, the more confident that I want to be about the population mean, the bigger the range of values or the bigger the interval will be. So if I want to be, what this means, it doesn't mean it has to be in here, but I'm 99% confident that the actual population mean is between 193.25 and 656.75. Okay? Or I could say I'm 80% confident that the actual value for the population mean is between 309.8 and 540.2. So the more confident I want to be in my answer, the bigger the interval is going to get. The less confident, the smaller the interval can be. Does that make sense? Now, your PowerPoint goes on to say the part of the expression that is added and subtracted, that z sub alpha over 2 times sigma divided by the square root of n, can be thought of as the maximum error in estimating mu. Mu is the population mean. Using the point estimate x bar with a specific level of confidence. The maximum error of estimation is also referred to as the margin of error, E. So, in some textbooks, after they show you the formula, like that, they would just say x bar plus or minus E. That would be like, the sample mean plus or minus the margin of error. All right, it's that in this case the E is z sub alpha over 2 times sigma divided by the square root of n. Now, one other way, and I'm just going to throw this out there because I've seen other textbooks teach the same thing. One other way that this answer can be written, you see the interval for 99%? What is the population mean symbol? It's the mu. This could be written like this. Mu is greater than or equal to 193.25, less than or equal to 656.75. It means the same thing though. So like writing in the interval form and writing in this form means the exact same thing. And it doesn't mean that the mean has to be there. We are just 99% confident that the actual value of the population mean is in that interval. All right, so one of the restrictions that we had was that our n, the sample size, has to be greater than 30 for this to work. Okay, so as long as n is greater than 30, we can find our interval by using that formula. We also have to know what the population standard deviation equals. We have to have a value. We have to know this. We must know this to get this to work. Because we don't have any population to find that value from. It has to be given to us. Okay? Now, if we don't have that value, then we have a little bit of a problem. All right, we have an issue if we don't have some of those values. So, if the standard deviation is unknown, That's the population standard deviation. Or the sample drawn is not normally distributed. Usually, though, it would say sigma is unknown, but or if the, I'm going to say the population is not normally distributed. Then this is a different type of problem. All right. This is known as a T-distribution, or some books call this a student's T-distribution. All right. So that's not a Z distribution because T is a different letter, right? So all the stuff that we've been doing with the Z scores and those Z tables goes out the window. Okay? A T value is equal to x bar minus mu divided by S over the square root of n. So it's not a Z value anymore if the population standard deviation is unknown. It is a T distribution. And in the real world, more times than not, we don't know the population standard deviation. Because think about it. If I'm doing research on some item, how am I going to collect data on everyone that uses that item in the world? It's almost impossible. So that would mean that I would have to use a T distribution if I don't know the population standard deviation, or a student's T distribution. So it's like the normal distribution. It's symmetrical. It's bell-shaped. But the tails on each end, like where it comes down on each end, it's a little bit thicker than a normal distribution. The T distribution looks more and more like the normal distribution as your sample size gets larger. So let me show you what I'm talking about. It's going to be kind of hard to tell the difference here. It's a couple drawn on top of each other. A couple bell curves, that is. All right, so you have the normal distribution. That's what we're used to dealing with, is the top one. The bottom one here, that's the student T distribution and what it looks like. Okay? And then there's another one drawn. There's a green one and there's a pink one here. So we have something called degrees of freedom that go along with that. And I'll tell you how to find the degrees of freedom. It's really easy. But as the degrees of freedom increase, that means the actual sample size is increasing. So the pink one here, or red, or whatever color that is, the degrees of freedom was 3. So you can see the tail is a little thicker here. As the degrees of freedom is 14, though, you can see that it gets closer to the actual normal distribution. So they have the same properties, it's just a different table. Okay? The degrees of freedom, that DF, that stands for degrees of freedom. That is equal to n minus 1. So where n is the sample size. So you can see how easy it is to find degrees of freedom, right? So if my sample size is 4, I have 4 items, my degrees of freedom will be 4 minus 1, or 3. Okay. Very easy to figure out degrees of freedom. However, very important that we can find degrees of freedom. Because if you look at table D, D is in delta. You can see that we have values in table D. Table D is in your formula packet. On the very far left, there is a column that says degrees of freedom. Okay, so we do have to use that in our table. Now, notice the other columns, they have a heading at the top. It says area to the right of the critical value. So that means, yes, we do have critical t values. Just like we have critical z values, we have critical t values. All right. So if we know that it's a t-distribution, and how do I know that? I don't have the population standard deviation. Then the main changes in my formula that I use to find my interval, this is the new formula. If it's a t-distribution, x bar plus or minus t sub alpha over 2. And I don't use the notation that your book uses because then it puts a little n minus 1 out to the side. And I believe that is to tell you the number of degrees of freedom that you have. I usually just write t sub alpha over 2, and then it's times s over the square root of n. Again, I don't put the little comma in the n minus 1. That's just too much stuff down there. That's too much there. I don't put that there. We find the degrees of freedom, then we'll be able to figure out a critical t value. Okay? And then we'll just plug the numbers in like normal. Now the only other difference, other than that's a critical t value, is that instead of sigma, the whole reason we're doing this is because we don't have the population standard deviation. So we have to use this right here. That's the what? Sample standard deviation. And let's just hope that's given to us, because if it's not, then we have to calculate that sample standard deviation if we have a sample. Okay? That was a long time ago when we started doing those, where you had to do the standard deviation. So technology is your friend on those. All right, so I'm getting close to the end times of this video, but I want to briefly go through a problem. This problem, I believe, is in the PowerPoint somewhere. If not, yes it is, but I'm going to put it up here anyway. All right. A simple random sample of hours worked in a week by student interns is drawn from a normal population with an unknown mean and variance. The 7 data values sampled are as follows. Construct a 95% confidence interval for the population mean. All right. So, we need a couple of things here. We need, what do we need? We need a critical t-value. We need an x-bar. We need a sample standard deviation. Well, I have one thing. What's n? 1, 2, 3, 4, 5, 6, 7. Okay, n equals 7. So at least it gave me that. Well, it has to give me that. Now, things that it does not give me that I need. Things that you would have to be able to calculate, whether you're using Excel or your calculator or by hand. You will have to calculate the sample standard deviation. You will have to calculate the sample mean because they're not given in the problem. All right. I am going to not do that now because I don't have enough time. And because that's, from like 2 months ago, how to calculate the sample standard deviation. I believe you can do that if you think hard enough. It's in there somewhere. But we should get on that 4.32 or somewhere about that. Okay. Now, X bar, the mean, add all those together and divide by 7. And it looks like when you do that, you get 23.45. All right. Now for the critical value. This is a very critical part of the problem because if without this critical value, you can't figure it out, and you've never looked one up before. It's the first time for everything. All right. So this is how you find the critical t-value. We need to know the degrees of freedom. The degrees of freedom, unless I'm looking at the wrong problem. Am I looking at the wrong problem? Well, I'm looking at the wrong problem. I was looking at another problem. So let me give you these values over. S is 7.08 and X bar is 29.86. All right. I just had the page turned over. Sorry. Degrees of freedom is what, though? 7 values. 7 minus 1. 6. Okay? Now, what was the confidence level? Or confidence interval? 95%. All right. So for a 95% confidence level, what is alpha equal to? Alpha equals 1 minus 0.95. What is that? 0.05. Our critical t-value is t sub alpha over 2. So that would be t sub 0.05 divided by 2. That's t sub what? I can do it in my head. Can you? 0, 2, 5. If you can't do that in your head, use a calculator. All right. So what that means is we're going to go to our table and go to your table D for critical values of t. Go to degrees of freedom of 6 and look for t sub 0.025. It's actually, here it's 0.025. So degrees of freedom is 6. It's the 1, 2, 3, 4, fourth column. So what is your critical t-value? 2.447. If you don't see that right now, you need to open your eyes and see that. Please, please, please. Ask the person behind you. Ask the person in front of you. But degrees of freedom is 6. Fourth column is in the column labeled T sub 0.025. So our critical value is 2.447. All right. We have everything we need now. Right? It's x bar plus or minus T sub alpha over 2 times S over the square root of n. So it's 29.86 plus or minus 2.447 times S. S is the sample standard deviation. Remember, that wasn't given. It had to be calculated. 7.08 divided by the square root of n. N was 7, so square root is 7. All right, so we need to punch that in the calculator. All right, and I'm going to take this out to about, it depends on how many decimal places I want to round to, but I'll take it out to 3 places. So 29.86 plus or minus 6.548. Now the reason why I'm taking it out to 3 places is because I'm going to round to 2 places. The same number of places that my mean and standard deviation were given at. So that's going to be 29.86 plus 6.548. So I got 36.408 and then 29.86 minus 6.548. And that would be 23.312. All right. So that is my interval. If I rounded to 2 places, I could say that I am 95% confident that the true value of mu would be between 23.31 and 36.4. So that is how you do a student t-distribution. It's not that it's harder, we just have to use a different table. Okay? And sometimes we have to calculate that sample standard deviation.